In this video, we're going to discuss the limitations on the performance of refrigerators that are imposed by the second law of thermodynamics. Here I've drawn a typical refrigeration cycle on the TS plot. The cycle goes counterclockwise, and it's below the temperature of a cold reservoir while it absorbs heat from 1 to 2, and above the temperature of some hot reservoir while it ejects heat from 3 to 4. First, let's define some terms about the performance of refrigerators. We know that conservation of energy tells us that the heat absorbed from the cold reservoir plus the work done over the whole cycle must be equal to the heat ejected to the hot reservoir. Now, in the case of a refrigerator, what we consider as the benefit, the point of running the cycle, is to cool the cold reservoir. So our benefit is QC. The thing that we need to input, or the cost to run the cycle, is the work input. So our cost would be identified as W, work in this case, and our waste is QH. If we want to make something colder, then we have to make some other place hotter, but we don't really care if we blow hot air outside the car or outside the room. So in terms of the cost-benefit analysis here, we're going to define a quantity called the coefficient of performance, or COP. One of the few variables in physics and engineering that everyone agrees should have 3 letters. For any refrigerator cycle, this is just going to be equal to the benefit divided by the cost. So heat absorbed from the cold reservoir, QC, divided by the work. This is similar to the efficiency of a heat engine, but it's not quite the same. Let's calculate the coefficient of performance for a Carnot cycle. In the Carnot cycle, the heat ejected to the cold reservoir is equal to the change in entropy of the cycle times the temperature of the cold reservoir, because that process is isothermal. The heat ejected to the hot reservoir is equal to delta S of the cycle times TH, because that process is also isothermal. So delta S here is positive in both formulas. It's just the overall width of the Carnot cycle on the entropy axis. This means that the work required to run a Carnot cycle refrigerator is the entropy width times the difference in temperature. Plugging these two in to the coefficient of performance, we get the cold temperature in the numerator and the temperature difference in the denominator. So the coefficient of performance of a Carnot refrigerator depends only on the temperatures of the reservoirs, similar to how the efficiency of the Carnot heat engine also only depended on the temperature of the reservoirs. But the dependence here for the refrigerator is a little bit different. The numerator is the cold temperature, so the coefficient of performance is lower if the cold reservoir is cold. That sort of makes sense, right? If something is already really cold, it's more difficult to make it colder. But the more interesting part is in the denominator. This is the temperature difference. The temperature difference only is required to be larger than 0. In fact, it usually is much smaller than TC. Think of TC being a room temperature and TH also being something around room temperature. TC would be on the order of 300 Kelvin, and your temperature difference between the cold and hot reservoirs might only be on the order of 20 or 30 Kelvin if you're refrigerating, say, the inside of a car. So this coefficient of performance can be much greater than 1, And it usually is for a good refrigerator. The answer is not always going to be as simple as it is for the Carnot refrigerator, but we'll see that the Carnot refrigerator provides an upper bound. So the situation is similar to what it was for the heat engine. The Carnot cycle gives us a limit about the best possible heat engine or the best possible refrigerator. In fact, in a moment, we'll prove that the maximum coefficient of performance for any refrigeration cycle is limited to be less than this value. The proof that the Carnot cycle's coefficient of performance provides an upper bound starts with the second law of thermodynamics. Let's look at this cycle again and assume that 4 to 1 and 2 to 3 are adiabatic. So we are only going to be concerned with QC, represented by 1 to 2, and QH, represented by 3 to 4. During the step from 1 to 2, the entropy of the cold reservoir will change. The cycle absorbs heat from the cold reservoir so the cold reservoir loses entropy equal to QC over TC. In that process, the change in entropy of the entire universe must still be positive. So we add the change in entropy of the cold reservoir, which is a negative value, to the change in entropy of the working substance. Here I'll write that as S2 minus S1. The second law says that this quantity must be at least 0. On the ejection step from 3 to 4, the hot reservoir gains entropy equal to QH over TH. Again, that ejection must be in accordance with the second law. So the change in entropy of the universe, which is equal to the change in entropy of the hot reservoir, plus the change in entropy of the working substance, must be greater than or equal to 0. In this step, the working substance loses entropy. So S1 minus S2 is a negative entropy value, but the sum must still be positive. Now we have two inequalities. Let's put them together. From the absorption step 1 to 2, we see that the entropy gain of the working substance, S2 minus S1, must be greater than or equal to QC over TC. I've just moved this, SCR, to the other side of the inequality. From the ejection step, 3 to 4, we see that the entropy difference of the working substance, S2 minus S1, must be less than or equal to QH over TH. I get to this by moving the SHR to the other side of the inequality and multiplying both sides by -1. That's how I get S minus S1, and that's how this turns into a less than. So now we have another sandwich situation here, where QC over TC must be less than the entropy width of the cycle, which also must be less than QH over TH. So only in the case of the Carnot refrigeration cycle would all three of these things be equal. For any other refrigeration cycle, there's some difference between QC over TC and QH over TH. This inequality clearly implies that TH times QC must be less than or equal to TC times QH. To put this in terms of the coefficient of performance, we'll replace QH by QC plus W. Then our inequality will become TH minus TC times QC must be less than or equal to Tc times the work input, W. If we rearrange this one small bit more, we will get Qc over W must be less than equal to Tc over Th minus Tc. This left-hand side here is the coefficient of performance. And the right-hand side is the coefficient of performance of the Carnot refrigerator. So no matter what the cycle is, no matter how cleverly you build your refrigerator, its coefficient of performance is always limited by the second law of thermodynamics to be less than this ratio of temperatures. Now let's discuss calculating the coefficient of performance for a specific refrigeration cycle. We have to be a little thoughtful about which steps get assigned to heat absorption or ejection and which reservoir we're actually absorbing from or ejecting to during each step. It's not as straightforward as the heat engine. Let's first look at a case where we have a counterclockwise cycle that looks simple on the PV diagram, but actually could not ever work as a refrigerator. This rectangular cycle has an isobaric step, an isochoric step, another isobaric step, and an isochoric step. It's one of the easiest cycles to analyze in terms of work. This is what it looks like on the TS diagram. Our isobaric stages are exponential with a lower slope, and our isochoric stages are also exponential but with a steeper slope. So what's the problem with this cycle for being a refrigerator? Well, a refrigerator needs to absorb heat from the cold reservoir on steps 1 to 2 and steps 2 to 3. That's where it's increasing entropy. That's where it needs to absorb heat. But the coldest point of the cycle is at corner 1. And afterwards, the working substance absorbs entropy and increases in temperature. The second law is the problem with this. It says that in order to absorb heat to move to the right on the TS diagram, we must be in contact with a reservoir that's hotter than the working substance. But the working substance is already hotter than the cold reservoir here, so it can't absorb any heat from the cold reservoir during stage 1 to 2. In fact, it also cannot eject heat to the hot reservoir during stage 3 to 4. So it can't do what a refrigerator needs to do. Wouldn't we be able to make this refrigerator work by considering a higher value of Tc? Let's draw a tentative line for a larger Tc value on our TS diagram, somewhat going through location 2. Now we see that we've resolved the problem of the stage from 1 to 2. The system, the working substance, can now absorb heat from Tc prime, the hotter cold reservoir, as it goes from 1 to 2. But there's a problem now with step from 4 to 1. Along 4 to 1, the entropy of the working substance is decreasing. Therefore, it must be ejecting heat to some reservoir which is colder than its current temperature. On the first half of this, that seems to be okay. The temperature of the substance is higher than the temperature of the reservoir, and so it can move to the left by ejecting heat. But once the working substance reaches the temperature Tc prime, it's now continuing to move to the left without any colder reservoir available. So this step here, that segment of the 4 to 1 process, is forbidden by the second law. It turns out there is not really any place that we can put the cold temperature reservoir on this diagram to make it actually work as a refrigerator consistent with the second law of thermodynamics. Now let's look at a cycle that works as a refrigerator and try to calculate its coefficient of performance. I've set up a cycle here which is composed of two adiabatic steps, which I'll just label with an A for now. Those are from 2 to 3 and from 4 to 1. The other two steps are isochoric, constant volume. I'll label those with a lowercase v, from 1 to 2 and from 3 to 4. Let's let the volume at locations 1 and 2 be equal to V1, and the volume at locations 3 and 4 to be V3. The hot reservoir is at TH and is in red. The cold reservoir is at TC and is in blue. Notice that this cycle looks kind of bizarre on the PV diagram because location 1 is below the temperature of the cold reservoir. Location 2 is at the temperature of the cold reservoir. And the system actually passes across TC on the segment from 4 to 1. We're going to calculate the coefficient of performance of this cycle by looking at the heat values, mostly on the TS diagram. Now it's easy to write an expression that is correct for the coefficient of performance. We just take the ratio of QC to W. This doesn't really illuminate the behavior of this engine at all, though. We would need to know the temperature of each corner. Let's try to express it instead in terms of the temperatures of the reservoirs. To get these expressions for T1 and T3, I've used the adiabatic relationship between volume and temperature. I've used the fact that volume 3 is the same as volume 4. I've used the fact that volume 1 is the same as volume 2. And I've also used the fact that TH is the same as T4 and TC is the same as T2. Let's define the symbol lowercase r as the ratio of V1 to V3. This is called the compression ratio, and it is larger than 1. If we substitute all 4 temperatures into the formula for the coefficient of performance, we can simplify it to 1 divided by the compression ratio to the power 2 over F minus 1. Now this coefficient of performance seems to have a sort of unexpected behavior. As the compression ratio increases, the coefficient of performance actually goes down. And as the compression ratio decreases, in other words, V1 and V3 become closer, the coefficient of performance goes up. So what's going on here? It looks like by just choosing two volumes that are close together and making a very small motion of the piston, we could achieve a coefficient of performance that's arbitrarily large. However, this illustrates why refrigerators always have a little bit of subtlety to them with the second law of thermodynamics. It's also the reason why the coefficient of performance doesn't tell the whole story. In order for this refrigerator cycle to behave like we expect, we made an assumption at the beginning, and that was that T1 was lower than T2, and that T3 was higher than T4. If we make the two volumes very close together, T1 will approach T2, and T3 will approach T4. The cycle will become just a degenerate back and forth adiabatic compression and expansion, which doesn't really do anything. So in addition to the coefficient of performance, we always also have to look at just the actual value of QC. Now let's write QC in terms of the temperature of the hot reservoir, the temperature of the cold reservoir, and the compression ratio. The amount of heat that's actually absorbed from the cold reservoir still depends on the amount of material in the working substance, moles, and both the temperature of the cold and hot reservoir as well as the compression ratio. Our assumption about this cycle was essentially that if it acts as a refrigerator, the value of QC is positive. In order for QC to be positive, we must ensure that the quantity in parentheses is positive. And that means that the compression ratio must satisfy this inequality. Or in terms of the compression ratio itself, it must be greater than the temperature ratio to the power F over 2. Any compression ratio smaller than this value for this cycle consisting of adiabatic and isochoric steps would produce a QC value that's negative. It wouldn't act as a refrigerator at all. Notice that if we plug in this limiting value, TH over TC to the F over 2 power, into the formula for the coefficient of performance, we would obtain the coefficient of performance predicted by the Carnot limit. On the surface, calculating the coefficient of performance is very similar to calculating the efficiency of a heat engine. But because we're doing a little bit more of a reverse operation in terms of the second law of thermodynamics, we're not allowed to make every step that we might want to. We usually have some inequalities on the values of R, or the values of the volume, that have to be satisfied in order for the cycle to actually act as a refrigerator.